So good morning, everyone. The first speaker is Dr. Peter Lunts from Harvard University. He will continue about HMC from yesterday.
Thank you very much. I think you keep this. Right? Yeah. Thank you for the introduction. And thank you. Thank you for coming back to hear more. Okay, so I'll be continuing talking about all the other details of our algorithm that I didn't touch on last time. So I think just to recap. Oops. Yeah, so just to recap, last time, the last thing I talked about was this sampling in HMC and how to collect good data, and then yeah, basically how to make your cost per effective sample the smallest. So today I'll talk about the other bottleneck of the method, the other part of the cost, which is this cost per operation that you do, which is this matrix inversion. So if you remember, there's this D inverse that you need to take. And I'll talk about the problems with that and what we do to solve it, to ameliorate these problems. And then I'll talk about how to actually measure fermionic correlations using HMC with pseudo-fermions, which is a little bit not straightforward. And then I'll discuss other potential issues or existing issues with the method and our solutions to them. So the key expensive operation that you keep doing over and over in this method is this matrix inversion. So if you remember in the action, yeah, so the part of the action that gets modified it looks like this. You have this complex bosonic variable bar phi, and then you have this matrix, this inverse of this matrix, fermion matrix that depends on phi, and then you need to compute this overlap. So here, as I was saying in yesterday's talk, D we're going to be assumed to be a positive definite matrix. And the complexity of this inversion doesn't depend so much on the size as it does on the condition number. So the condition number of a positive definite matrix is just the maximum eigenvalue divided by the minimum eigenvalue. So if you have absurdly small eigenvalues, like you do in a gapless system, this number is going to be very large. So the colloquially, what you expect in general from the lore is that if you, in the order of increasing condition numbers, the fermionic systems are as follows. You have gapped fermions, they have the smallest condition number, no gapless modes, and then nodal fermions, and then they can go critical, and then if you have a Fermi surface, it's even worse. And the worst case scenario is where you have a critical Fermi surface. So the Fermi surface interacting with some critical bosonic fluctuation. And this last scenario is the one that I'm always in. So all the examples that I have are applied to this worst case scenario. And the way that we invert this, the way that we solve this equation is with an iterative procedure, some iterative method, namely conjugate gradient. You don't have to use it, but that's what we use. And so, of course, you don't actually compute the full matrix, the full inverse D inverse. What you actually want is the application of this D inverse times a vector. That's all you care about. And so in this conjugate gradient iterative method, the number of such iterative steps that you need to solve this equation to a given error that you desire compared to the error that you start with from some initial guess scales as follows with the square root of this condition number. So as I'll mention a bit later, as I mentioned last time as well, oftentimes we work with the case where this D matrix is actually in a form that's explicitly positive definite, where some d tilde dagger, where d tilde is maybe a matrix of half the linear size, or some spin resolved thing, flavor resolved thing, and then then the condition number that I'm talking about here is not KD, but can be expressed as KD tilde squared. So number of CG iterations, if you fixed your error and you ask how many CG iterations do I want, that number scales as the condition number. If you're looking at it in this form, it goes like, or the condition number squared, depending on how you formulate it. But the number of iterations is linear in this object here. So there might be a typo. Yeah, what I mean is KD tilde, not KD tilde squared. Okay, so this is the technical problem that we're faced with when we're trying to do these calculations all the time. And this number can be quite large, like it can easily reach tens of thousands very quickly. At criticality, I'll show some numbers later. So it really helps to try to solve this problem in some way. And so what you can do to help you ameliorate this issue is find a good preconditioner. So what is a preconditioner P? It's some matrix. So here, let me focus on this formulation where the matrix that we're trying to invert is DD dagger, just to be explicit. So P is some matrix that basically you apply P inverse to this equation here. Just to apply P on both sides, for example, and then what you have is the following. So the solution that you want can be re-expressed as this P inverse times this matrix. And now you can say, okay, maybe I can instead solve this problem here. The idea being that I want now this matrix P DD dagger inverse to have a much smaller condition number, or DD dagger inverse, DD dagger P inverse. If that guy has a much smaller condition number, then solving this part is much easier. And then also, if my preconditioner is such, since I picked it, that the inverse can be easily computed, then this whole thing simplifies. So then I don't have to worry about this part. I just have to invert this. Sorry, I wrote it a little bit funny, but I just have to invert this DD dagger P inverse. And so ideally, what you want is actually for this P to be exactly DD dagger inverse. If that's the case, then this is the identity and it has condition number 1. So you want P to be, or for example, you want it to be the diagonalized version of DD dagger. That would be the ideal scenario that would make the number of CG iterations you need to be 1. And so we have considered 3 different preconditioners that work well in different scenarios. So the first precondition that we considered that I'll discuss briefly is the free fermion preconditioner, which we used here. And in these 2 papers, so in this paper, we use this Jacobi preconditioner, and in this one, it's a technical paper. We talk about this multi-grid preconditioner. And an important note is that all of our matrix inversions are done on GPUs, and this is, from a technical perspective, a huge advantage. Because there are basically a bunch of matrix vector multiplications called matvecs that need to be done. That's the core mathematical procedure. And on a GPU, these can be massively accelerated using certain tricks. Okay, so the first thing that I'll mention is this free fermion preconditioner. So the idea is just to use this non-interacting part of the fermion matrix as the preconditioner. Okay, so if your D matrix has this form, K, which contains all the free fermion part parts plus this G times V. V is this interactions with the Hubbard-Stonbridge field, and G is some schematic coupling strength. Then you can use, DD dagger is like K dagger plus stuff that's order of G. And then we can say, okay, well, why don't we just use this first part as an approximation for DD dagger? That's the idea and spirit. And then we'll just set the preconditioner to be this guy. Sorry, this should be, yeah, we'll set it to be this guy. Yeah.
So, KK dagger is sparse.
K dagger is
It's a sparse matrix.
It's still sparse, I think.
But then P-1 is dense.
Yes.
So when you multiply, and so that's a huge beta volume matrix. And when you go back and you do the P-1,
But the point is that K, so I didn't write this on the slide, but the point is that K can be fast multiplied, or K inverse can be fast multiplied with fast Fourier transforms.
okay, so that's what you do after.
Yes.
Better like this.
Yeah. So you can just go to Fourier space. Yeah. And so just to give you an idea of how well or not well this works, so here we can plot, we can multiply P inverse times DD dagger to see how close it is basically to the identity, or at least look at its spectrum. Look at its the condition numbers of that at criticality. So this example is for this is for the clean spin fermion model example that I was talking about yesterday. So if you remember, there are two example theories that we applied this to. Both are the spin fermion model. One is the clean case, one is the fully disordered case. This is the clean case. We're sitting at the critical point, and so here you can see at two different temperatures, for example, what happens to the condition number of this M matrix. So if you don't precondition, if M is just this DD dagger, then you can see that the condition number here, this is over some ensemble, so it's a histogram, but it's centered somewhere around like 3,200 or something. Then once you precondition with this P, the product has condition number like 50. So it's a huge difference. And then when you go to beta equals 10, it gets much worse. So the condition number of the unpreconditioned matrix is like 11,000, whereas that of the conditioned one is 250. So this is a big speed up. And so there are two things to note. That first of all, the condition number of M, regardless of whether you're looking at the unpreconditioned or the preconditioned matrix, they both scale as beta squared. So you can't get around that here. And then, the other thing to note is that, of course, this works well if G is not too large. Once G becomes too large, then this becomes a bad approximation for the low-lying states. It just won't work. The unpreconditioned one will actually be faster than the preconditioned matrix to invert.
So in this particular case, the K is just the tight binding part, the free fermion part.
The K is just the tight binding part, including the frequency contribution.
Sure, I see.
What about Km as a function of volume?
I don't.
So the question was, as a function, so why beta squared? Is that empirical? You can show it. That's not clear to me.
That is empirical. I don't. Yeah, I'm not sure how to show it rigorously.
Okay. And the volume.
So the volume from the previous results. I'm not showing this. Sorry, but remember the scaling of the cost of inversion scaled only linearly with volume, as like it was optimal already. What we want is for the cost to scale. anyways, so yeah, so this is the case. So this works well when G is not too large. And what happens if you increase G? So here, these are for where G is like 1 over square root 2 or something, which ends up being some, 1/8 or something like that of the bandwidth. So it's not perturbative, but it's still not as large as maybe you want to increase it to. And also what matters is the effective G, the effective coupling between the fermions and the bosons, which kind of depends a lot on the physics. So in the case when G is large, what we did is so what you can do is you can focus only on the diagonal. So if G is large, then you can say, okay, let's write the diagonal of DD dagger. It's this has this form. It's the diagonal of KK dagger plus this form which goes like G squared times the square of this phi field, the bosonic order parameter field. So this is some just one-dimensional array. And then what you can do is so using only the diagonal as a preconditioner is called such a preconditioner is called the Jacobi preconditioner. And this is what we use in Spirit. So I'm calling this P tilde J because this is not the actual one that we use. So if you want to be more it doesn't work as well as the more advanced versions, which is some weighted Jacobi with smoothing. In that case, so this is the actual preconditioner that we use. It's in Spirit, so the inverse of it is in Spirit this diagonal DD dagger, but then there's some smoothing, a few iterations they need to do of smoothing with this smoothing factor W, and yeah, we take some value for it, and this this is much more stable, and it helps a lot with the condition number for larger G. So we tested this for the disordered case of the spin fermion model, where the effective interactions are much larger. Basically, since there are no everything is disordered in real space, the interactions are all-to-all momentum space, and the whole Fermi surface is critical. And so the effective interaction strength is larger. So this is necessary. This was necessary for the disordered case. It made a huge difference in the wall clock time of the inversion compared to the free fermion preconditioner. However, this does not address the fact that the scaling of this condition number still scales as km squared, as a beta squared. So still scales exactly the same, just the prefactor is different. So in order to address that issue, so the scaling with beta, what you need to do is you need to do some kind of coarse graining procedure. So and that's done with this adaptive geometric multigrid, which I won't talk about in very much. But the idea is basically that if you want to beat this scaling of beta squared, you need a preconditioner that coarse grains the matrix and systematically removes the near zero modes, which are causing you problems. And for this, we use this multigrid V cycle, or in reality, we only use 2-grid. But you can go further. So the coarsening here basically only happens in the time direction. This is because we have near perfect scaling in the real space volume anyways, and plus coarsening Fermi surface is much more complicated. You need to do something like Shankar RG. So we just coarse grain in the time direction. With the idea being that these residuals are on the fine lattice are passed down, are smoothed and then passed down to some coarse lattice, where they're solved very approximately using lower precision. And then these residuals from this conjugate gradient from the coarse lattice are, from the coarse lattice are then propagated upwards back to the fine lattice and used to augment the solution on the fine lattice. So in principle, kind of this goes into the matrix, finds the near zero, the near null vectors, finds your near zero modes, and it kind of does exactly what you want. And that's why, in principle, this method actually does exactly achieve the desired scaling which is linear in the whole matrix size. So it's a beta V. So rather than scaling beta squared V, it scales like beta V. However, there is a caveat, which is that building this preconditioner from scratch for every new configuration phi is expensive. And so that kind of eats up a huge overhead. And so, but in practice, what you can get away with is that you don't, as phi is being changed from Markov chain configuration to Markov chain configuration, you don't need to rebuild this preconditioner from scratch for every new phi. Because they're close enough, they don't like get updated so rapidly that this preconditioner becomes bad. So you can get away with doing it only once in a while. Maybe roughly, I don't know, we've kind of tried 50 iterations, and it still works well. So yeah, I'm not going to say more about this. This is still in testing for like all the exact scaling and benefits that we get. But this is our best preconditioner at the moment. Definitely the most sophisticated one. Okay. So that has to do with the computational bottleneck, the matrix inversion. Are there any questions about this? Okay, so then if not, I'll talk more about how we actually measure things in this HMC algorithm. So this has to do with the fact that we can't actually measure it straightforwardly. We can't measure fermionic correlators straightforwardly like we do in the BSS algorithm for the reason that I'll explain. So like I said, if you want to measure some correlation function of fermions, so some fermion-Green's function or some current operator or overlap, then this requires more work. And the reason for that is can be shown with the example of a two-point correlation function, which is the Green's function. So if you have some two-point correlation function like this, where I and j are some arbitrary space-time indices, then this is given by the inverse of d at sites or space-time points ji, and the expectation value of this with respect to phi. And in the BSS, you just have this object. Here, d is then the compressed version, but you still have this object. But we don't.
With respect to var phi.
No, with respect to phi. Here.
Phi is the Hubbard autonomy, is a physical field.
Yes.
Var phi is a pseudo fermion.
Yes.
So you average over the pseudo fermion.
No, you average over the Hubbard-Stratonovich field to get the Green's function.
And so what happened to the var? So you
it's not there yet. I haven't introduced it.
Okay. Sorry. Yeah.
Sorry. So this form is kind of just universal. It doesn't know anything about the exponentiation or not. I'm just stupidly not compressing this d for the moment because I know that in a second I'm going to exponentiate. Yeah. So since I don't know how to compress things in this BSS form, this is, and furthermore, I just don't have that object, even if I did know. This is what I have to do is I have to, then if I want all of these ji, I have to invert this full matrix D inverse. So this costs some exorbitant amount of compute, scales like this, and tau, so the number of time slices, so this is just like beta volume cubed. So I definitely don't want to do this to compute the Green's function. However, if I'm only computing, for example, in this specific case of the Green's function, if I'm only computing the diagonal in momentum and frequency, so if I'm only computing the diagonals in the Fourier space, then I can compute this in almost linear scaling in the following way. So let's say I just want the Fourier components, because I know that my system is translationally invariant, and that's all I care about. Then this can be expressed as the diagonal of this D matrix in the Fourier representation, of this D inverse matrix in the Fourier representation. And then I can use the following trick, which is pretty standard in applied math, where you compute the diagonal of a matrix stochastically. So here, this is just the notation for the expectation value of the following thing. So here, I'm multiplying this vector V. I'm sandwiching basically this inverse D matrix between this vector V in the same way. So this is just some number, and then I compute this expectation value. So what is V? V is a vector of plus and minus ones. That is, so it's a random vector of plus and minus ones that's drawn from a flat distribution. Okay. And then E, is the expectation value over this flat distribution of V's. So this is some identity, some mathematical identity that now I'm going to use to express the diagonal, to express specifically these the Fourier components of the Green's function in the Fourier space. So yeah, so that's how we're going to do it. And so what I wrote previously was for a single phi configuration. But actually, in computing the expectation value of this object, if I want, let's say, D inverse at omega and k of phi averaged over phi, I can sample both. Simultaneously. So in other words, as with var phi, we can now interleave the sampling of your Markov chain, of your MCMC configs, and this new random variable V, which is just plus and minus ones. So then the expectation value of phi becomes approximately, so that the mean with respect to your Markov chain configuration, and NS here is the number of samples of your phi field that you have, phi S. And then you take some fixed number of these random vectors V, some number of NH. Capital H stands for Hutchinson, because of this Hutchinson trace estimator. And then you pick for every new config, you pick a fixed number NH of these V's that are fresh. So they depend on this config. So you redraw them. Yeah.
The D minus one is in real space. When in the code. So you do a fast Fourier transform of the D minus one, and then you apply your Hutchinson trick.
Yes.
Is that correct? So that there's a missing fast Fourier transform.
Yes.
And the equation
I was very sloppy here with the fast Fourier transforms.
The hat indicates the fast Fourier transform.
The hat
the Fourier transform.
The Fourier transform is the hat.
Yes.
Good.
But
So then
I was sloppy here with the fast Fourier
okay.
transform.
Good. Okay.
I
just wanted to
K space and real space. Sorry. Yeah.
That's okay.
So this is it's
but for each this phi field configuration, the system is not translational invariant.
For each one,
Yeah.
it's not, yes, but I know that I in the end, so D inverse this
Right.
expectation value can be computed for off diagonal terms as well.
Right.
I just know that I don't care about them. So in the end, I am focusing only on the expectation value. I don't use the fact that I don't assume that the off-diagonal terms are small for each configuration. There's no such assumption here. Yeah.
But you won't be able to use that to calculate 2-point correlation functions then.
No, I will. I'll show you. I won't, not this exact fact, but
Okay,
I
okay,
will
okay,
rewrite
okay.
it as the diagonal of some matrix.
So again, so for each, you have two sum, the sum of n hat, nh, you assume the field is translational. You just do the Fourier transformation and assume the system is translational invariant.
I'm assuming it in the sense that I'm only calculating a particular thing, but my calculation is not biased by this assumption. That's what I'm trying to say. If I knew that it was not translation invariant, I would just compute more stuff. But
I see.
This expression is for how it's written is correct. It's just that this is a cheat. I'm saying omega k, it should also be omega k, right? That what I mean is the diagonal of this guy in Fourier space.
Okay.
Yeah. So in practice, this NH, so this NS is fixed. It's like the number of Markov chain configurations that you have. And this NH is what you choose. So however large you need it to beat down the extra variance coming from this extra stochastic calculation. So in practice, we choose it to be like between 1 and 50 for all the observables that we compute. So this adds a cost, right, of NH, a prefactor cost of NH to every calculation of your Fermionic observables. So it's expensive. On the other hand, this all happens post-processing. So you can select fewer phi configs that you know are decorrelated. So you don't do this on the fly. So wasting time with correlated configurations, you can do this after the fact and select, yeah. Oh, whoops.
Excuse me.
Yes.
When you are only interested in the case.
When you are interested only in the case where omega and k is 0, then can for that case NH can be reduced much less. Actually, actually, due to the existence of translation symmetry, then the how to say it's a kind of how to say randomization can happen automatically.
Yeah, so, it sounds plausible, but the point is that they're all computed simultaneously by construction. You can't pick it out because you see this array is written as the diagonal of something, of some matrix, and the diagonal, the full diagonal is what is approximated here. So for that, to get each component of the diagonal, you have to do these products. I guess you could separate them out, and maybe try to use smaller number for that component. But yeah, we were always interested in the full low-lying excitations, right? So we never.
Okay, thank you.
Okay. So yeah, so in the end, the new variance that you have will be a sum of these two variances, that come from this additional estimator. So the total variance is this Monte Carlo variance and this what we call Hutchinson variance. Okay, so that was the example of the Green's function. But what about other operators that are higher order fermionic correlators? So, for example, this current correlation function is very important in condensed matter physics. It's used to calculate the conductivity and the superfluid density. So the real space current operator, assuming no flavor indices or anything like that, is written as follows. So it's psi dagger psi with some hopping terms. And then what you're often interested in is this current correlation function lambda. A here is the subscript that indicates the direction. So you're interested in like lambda x to compute the conductivity in the x direction, for example. And you usually compute this in Fourier space. So that's this correlation, this current correlation function. And then this can be written in this form. So this is so here trace tilde is a normalized trace. And then you can write it as trace of some fat operator times plus the disconnected part, which is the product of traces of smaller operators. So here J is this like the actual matrix operator that corresponds to this current operator here in terms of psi dagger psi. So J is like the matrix representation, and D inverse is the fermionic matrix. So that's the same thing that we were looking at on the last slide. So this is so D inverse. So J here is just a matrix. So this is some 4-point correlation function. So this is used, for example, in the calculation of the conductivity. So if you're looking at the conductivity in the x direction at some finite frequency, then sorry, this should be q equals 0. Yeah, sorry about that. So then this is basically just this current correlation function computed and then with some kinetic energy operator as well. So this is some one-body part. But the point is that in order to know the conductivity, you need to compute this object. Same thing for superfluid density. It's defined in a two-dimensional system as follows. So again, you need to compute this object. And higher order correlators in Monte Carlo are notoriously more noisy. But then if we apply the same procedure,
sorry, could you just explain me more about this current correlation function formula? Because what is the J A I omega Q? Is it only a coefficient or it is a correlation function?
This big J?
Yes.
The big J, sorry, is a matrix. It's a matrix. So if you were to create if you were to go with the Fourier space, so if you were to create a matrix from these guys, from these coefficients, like IT, I plus N, etc.
I see.
So it's like the one-body part of this many body operator.
Okay. So is it just a like decomposition?
Yeah. So this is just a rewriting. So this. Sorry, I'm having trouble with this mouse. Yeah. Okay. So this guy is just a rewriting of this correlation function in a way that writes it explicitly as a trace of some matrix, some operator.
Okay.
So yeah. So what's the point of this? Sorry. Yeah, this might be a little bit confusing. So the trace is just the sum over the diagonal, right? So
yes.
Therefore, you can apply this formula. So if you write it as the trace, then it's the sum over the diagonal, and you just apply this formula, and then so that allows you to apply it straightforwardly. Okay. So you apply it to each component. Here, everything that has a trace, you compute using this stochastic calculation.
I think I get a point.
I'm sorry?
There's a question on.
Yeah, hi. So do you need to, I mean, is this only the bubble, or can you also evaluate vertex coefficients using this?
This is exact. This is not perturbative. I'm just rewriting.
So you don't need... Okay. Yeah. Okay. Thanks.
Yeah.
I'm still a little bit confused. I understand that you do the Fourier transformation to get to the diagonal elements of the final answer, because you know that all the off-diagonal terms will have to average away. But then here, why is it allowed to use the same frequency in both current terms? Because from like you're essentially looking at a bosonic correlation function. So you would want to have the bosonic frequency, Matsubara frequency, but you can split this in different ways, can't you?
What do you mean split it in different ways? So yeah, you're
So
correct.
if I think about the first term as a bubble, then I know that for the current correlator, the outputting frequency.
Omega n is just a bosonic frequency, that's it.
Yeah, sorry, this was a little bit confusing. Omega n is bosonic. So J is a bosonic correlator, and this is just the definition of what we are computing. So this first equation
I
is
see.
just the definition.
I see.
So I am still confused.
Sorry.
So this is for a given field configuration? No.
Yeah, so this is for a given field configuration. You rewrite it as follows. Yeah. So
if you put this is an equation you write for a fixed background field configuration.
yes.
Then somehow I disagree because
yes, there's some additional.
I mean, I just start with the first one, right? Because the trace is over. The trace is not so. There is a sum over the field configuration somewhere outside of which is not written but is implied.
Yes.
Right. So now for a given field configuration, you don't have any symmetries. So you're not allowed to do the Fourier transform and assume translation invariance in space and time for a given field configuration.
But I'm not assuming this to rewrite this trace.
But you can still do a Fourier transformation to switch your bases. And if you don't have translation symmetry, you get
but then
matrix.
but then you don't have minus I omega n in the second JB.
That's fine. But you can still look at the diagonal elements of this matrix that you generate because you know that if you start averaging over all the other configurations, the off-diagonal part vanishes.
Okay.
So think of this as specific subsets of elements in a larger matrix.
You're right. Okay, perfect.
Okay. So these are some examples of higher order fermionic correlation functions, which we want to compute. And yeah, so we computed these. So I'll show some examples. So this is the example of these fermionic correlation functions. So here, the example that I'm drawing on is our application of this to the spin fermion model with fully disordered Yukawa interactions. So here, these are like the physical results. So this is the calculation of the Green's function. So yeah, sorry, this is the calculation of the imaginary part of the self-energy on the Matsubara axis, which is computed from the Green's function. So here, of course, we also separate, this is a subtraction of two large quantities, which are on the order of this black line here. And, to get a small quantity. And so that's notoriously a bad idea, right? But here, of course, we're forced to do it. But despite this fact, we have extremely smooth data. So this form of the self-energy in Matsubara frequency, so yeah, first of all, I have to make the point that this is the fermion Green's function averaged over the entire Fermi surface. Okay, so here in this theory, the momentum dependence of the self-energy is absent due to the structure of the interactions. It doesn't care about momentum space. So we can average, and then the number of these Hutch vectors that we use here is 30. Okay, just for, we just chose this number, it looked fine. So of course, if we choose a larger number, then we reduce these error bars. But we stopped here. And what you can see is that at different temperatures, this is at some value of the mass parameter that's inside of our critical phase. So we have a critical phase instead of a critical point. This is somewhere in the middle. So the theory is strongly coupled here. And you can see that the fermion self-energy has a super logarithmic marginal form. So it fits very well to this omega log omega plus omega log omega squared. And so here we plot this functional form, the data as passed through this functional form versus imaginary part of self-energy on a very straight line.
What's the
Um,
ratio between the coefficients A and D for the log and log squared? Is the log squared substantial, or is it kind of a small correction?
Yeah, the log squared is it's in between. It's smaller than the other coefficients, but it's not negligible.
I see.
Yeah. Yeah.
The temperature is in units of the log.
Yes, sorry about that. So here the nearest neighbor hopping is set to 1. That's our everything is in units of the nearest neighbor hopping. Yeah. And then what we also did is we computed this some AC transport. So so we computed this conductivity, and from this conductivity we extracted the AC scattering rate, AC transport scattering rate, gamma. Gamma is like the difference between so it's the inverse of the conductivity minus the inverse of the free conductivity, which is finite for finite frequency. And this is, sorry, gamma trace. So the AC scattering rate, transport scattering rate, sorry, gamma transport, AC transport scattering rate divided by this Drude weight, d tilde. So this tells us also about the transport physics, the physics of transport. And here we can see that, so first of all, on a technical level, here, this is already spatially averaged over all of space, not just the Fermi surface. And so we can get away with fewer number of Hutch vectors. So despite the fact that this is a higher order correlator, we use only 10. And then, so you can see again that at various temperatures, this is our data. You subtract 2 large numbers to get a small number, and it's extremely smooth. Again, it fits onto a very similar functional form, indicating that the transport also follows from this super logarithmic marginal Fermi liquid physics.
So here, yeah, this is very interesting. Here, let's say for the left one, if you go either to the Fermi, I mean, actually both sides of your phase diagram, which I think that's your lambda tune yourself to the critical point.
So this is the disordered case. There's no critical point. It's a critical phase.
That's fine.
Yeah.
But now if you go to the Fermi liquid phase,
yeah.
what do you get from cell energy?
Yeah, we actually, yeah, we don't know. It's a crossover. It's a slow crossover to a Fermi liquid. And in the middle, we didn't go far enough to kind of see an explicit Fermi liquid form.
Right.
So it's some kind of crossover function that is not super well fit by, it kind of can be equally well fit by some marginal Fermi liquid or Fermi liquid form. But it's clearly something in between. And here I'm showing this at this value of the mass parameter. This is very clearly a better fit than the Fermi liquid, and it's very, very good. Whereas further closer to the Fermi liquid side, it's not that good. So that's the.
But if you go deep in the Fermi liquid, right?
Yes, you should just get
a linear omega.
I guess you would get linear plus quadratic because this is the Matsubara frequency. So on the Matsubara axis, you would get linear plus quadratic. Then it should just be the clear winner.
But you see that.
We didn't go far enough to see that.
I see. Okay. Yeah.
Another question from Afar. So is there a way to evaluate the effective mass here, or I mean, do you get resistivity which is T log T or just T?
Yeah. So here I'm only showing the AC data. To get the DC data, you need to do some extrapolation to zero frequency. Yeah. We do. So here at these lambda points, at these mass parameter values, I forgot either we get a T linear resistivity, AC resistivity, and sorry, DC resistivity and DC scattering, DC single particle scattering rate, or we get a T log T. I forget if it's at this value. So in our phase diagram, in the critical phase, we have t or t log t, depending on which lambda you have.
Okay.
Yeah, here I think you get this t log t.
Mhm.
Okay. Yeah. Okay, so that's, sorry, I mixed these up. Yeah, so I went through the fermionic correlators here. So that kind of summarizes all of the current work that we've done, roughly speaking. And now I'll talk about some of the issues that are intrinsic to this method and that we're trying to tackle one by one. Yeah.
For the self energy, right? This is very beautiful data. What's
you.
the system size here, and
40 by 40.
and I see, and how expensive is this? I mean, how?
To collect the data?
Yeah.
Yeah, so this is just with quench
And
disorder.
number of disorder realization is how much?
So the number of disorder realizations is 10.
Uh-huh.
And we run kind of 10 separate MCMC chains.
Right.
One for each disorder realization. I think it takes like, I want to say 4 days in warm up, and then we collect data from each chain for like 8 days.
I see.
We don't, yeah, and then this calculation of the at the lowest temperature, yeah,
Right.
I'm all talking about the lowest temperature here.
Sure.
And at the lowest temperature, this additional calculation of the fermionic correlator is like a day, 24 hours.
I see.
Yeah.
Okay.
Everything is done on GPUs.
Right.
So every chain runs on one GPU.
And the warm-up time includes all of this auto-tuning and so on. So
Yeah.
the auto-tuning part takes roughly 4 days that you have to invest.
For the lowest temperature here, yes. Yeah. I think, yeah, that was the case.
Okay, thanks.
Yeah, that's why. So like I said, we're looking at better things to, like, better ways to optimize the warm-up, like using this no U-turn sampler. That's like a different way of sampling, but it should reduce the time of the warm-up by a lot. Yeah. Okay. So the issues. So so the various issues that I'll talk about are as follows. I'll talk about the odd number of the issue of this when you have an odd number of fermion degrees of freedom. And then I'll talk about ergodicity issues, which Facher and company studied in a revival of this method. And then I'll talk about the problem with various ordered landscapes or quasi-ordered landscapes. So, as I mentioned in the beginning of the lectures, sometimes, despite the fact that the determinant of D of your fermion matrix is positive definite, the matrix itself is not positive semi-definite, and you must resort to using this formula. So in general, the matrix, if the determinant is positive, you can always rewrite it as a determinant of the square root of dd dagger. So dd dagger is a positive definite matrix, so you're happy there. But now you need to invert the square root of it, which is a hassle, so to speak. So you have to bite the bullet, and one way to do this is using the representation of the inverse square root function as a geometric series, which comes from some complex contour integration theory. There's some paper, for example, that works this out in 2008. It's some math paper. And so then what you get is you have this, so if you have some general positive definite matrix A, and you take its inverse square root function, then schematically speaking, this is some sum over some finite number of terms that you determine with some coefficients, and then you invert. You're always, for each term in the sum, you're inverting your matrix A plus some offset times the identity. So this offset is always positive, and these A coefficients. So these offsets are always positive, and furthermore, they are fixed for every basically power here. So if the square root here is the only thing that you're computing, then these lambda i's are known to you from some calculation that you have to do once. It's already done for you, actually. So then this is the whole thing that you do, and naively, this is just doing the same thing that you were doing previously in inverting this A matrix, but you do it n times. So there's an overall prefactor that you pay for doing this inversion of the square root, but it's a constant. It doesn't scale with system size. And furthermore, the scaling is not actually linear in n, because basically, so when lambda I, so the first few lambda I, let's say they are small, they are in the order of the lowest eigenvalues of A. And those such inversions of A plus lambda j times identity are about as expensive as the inversion of A, because they have about the same condition number. But then the lambda I for larger j values start growing. And then once that happens, this whole shifted matrix has a much better condition number. And so that's a cheaper calculation. And so this doesn't actually increase your calculation by a factor of n, or by some smaller number. Usually maybe from talking, so collaborator Mike Lindsay estimates that about factor of 5 or 10 realistically, which is totally doable. And the nice thing about this approximation is that it converges exponentially fast in n. Yeah. So that's ongoing work with Henry Shackleton, Mike Lindsay. It's in progress. So that's just some generic methodological development that will help this method be applied to basically any sign problem-free theory, sort of. So the next problem, which again has to do with applying this method to various types of theories, is that there are some models for which this method actually breaks ergodicity. This was first pointed out in this paper by members of this group here. So, for example, in the canonical case of the half-filled repulsive Hubbard model, sign problem-free condition on this fermion matrix can be written in this form. So the determinant of D can be factorized into the product of determinants of smaller matrices, which are spin resolved. And then this is, since these matrices at half filling are proportional to each other, then this can be written as determinant of one of them squared. And the determinant of, so if you pick an appropriate Hubbard-Satonovich field, then this determinant is always a real number. So what this means is that even though this object is always positive definite, there are certain configurations of the Hubbard-Satonovich fields which make this positive, and certain ones which make this negative. So therefore, you can draw some imaginary boundary between these regions where your determinant, so your single determinant is positive or negative. So here, this plus plus means that the overall determinant is positive because it's a product of two positive numbers, whereas here it's positive because the product of two negative numbers. And the issue is that to go between these two, there's a boundary necessarily where the determinant vanishes. So there's a boundary configuration space where the determinant is 0. And by construction, the HMC trajectory can never cross this barrier. It's, in other words, the potential energy term in the Hamilton-Jacobi equations diverges. So specifically for the Hubbard model, there's one way around this is to use this fierce ambiguity. So if you take the Hubbard interaction and you can decouple it into the spin channel that you used previously, but then with some weight 1 minus alpha, but then also in the charge channel that you don't want to use, I guess, if you have a sign problem, with some weight alpha. And alpha is some number between 0 and 1. And the point is here that even for a small alpha, like 0.01 or something, for the system sizes and parameter values that were studied in various papers by members of this group, the HMC, so let me just step back. The point is that once you decouple in this charge channel additionally, when you use a Hubbard-Stojanovic transformation to decouple this interaction, you are forced to complexify this action. When you complexify this action, this matrix becomes complex. Now you're allowed, your HMC trajectory will go around these boundaries. And for even a small alpha, it was observed that HMC will indeed restore ergodicity. So this is one way for a specific model to get around this.
So, but you could also do other things, right? I mean, you could also, there was this, you could do some type of a global update by proposing like with a Langevin step, something like that, and then accepting and rejecting this global update.
Yes.
So because this is very expensive and not always feasible.
Yeah.
I mean, there are many possibilities to overcome this. That's a comment actually.
Yeah. Yeah. So this is the previous thing that I was talking about was a generic solution to a generic problem, and what I'll talk about here is more of like a specific solution to a non-generic problem. But yeah, as Fakir mentioned, there are other potential ways around this, but we're going to draw inspiration from this way for the problem that I'm going to mention now. So the specific model that I have in mind where this issue is present, besides the half-filled Hubbard model, which is of interest to me, is there's this theory of the Ising pneumatic symmetry breaking in a metal. And this model has a sign problem-free lattice realization and was studied in these works by Shatner and company. So roughly speaking, the interacting part of the action has some strength of the Yukawa coupling, G, and then the fermions, which are spinful, are coupled to this phi field, which kind of mediates, if it condenses, it mediates asymmetric hopping on a square lattice in the x and y directions. So then this phi is this Ising pneumatic order parameter, and lambda is its, which I'm not writing, is its mass parameter. So here, when the mass of this phi field is very large, its fluctuations are damped, and it doesn't have any effect on the fermions, on the shape of the Fermi surface. But then, beyond some critical point, it condenses and it warps the Fermi surface. So depending on the sign of the condensate, it will either distort the Fermi surface in the x direction or the y direction. Yeah, for some reason it's not drawn very well. And here, the sign problem-free condition comes from the same form, that this action doesn't care about, this interaction does not care about spin, and the theory is real. And therefore, again, the determinant can be written as the product, and you have this, again, same plus plus and minus minus. So what we want to do is we want to take a similar approach as was done for the half-filled Hubbard model. And here the idea is, what we're going to do is we're going to augment the action with an additional field, additional Hubbard-Standard field, additional auxiliary field, called phi tilde. And phi tilde mediates some strange looking interaction, which just ends up being, in the end, an attractive density-density interaction. But you can write it in this form, and then if you write it like this, then this I and minus I imply that the determinant here can be written as det m up, det m minus, and then det m minus is the complex conjugate of det m plus. So that means that the sign problem precondition is still present, but the action is now complex. And the idea is that if we only care about points in parameter space where this mass parameter lambda is close to its critical value lambda c, then what we want to do is we want to take lambda tilde, which is the mass of this secondary auxiliary field, to be very large. We want to make it massive so that it doesn't participate in the lower energy physics that we're interested in. And so ideally, we want to make it actually infinite. In practice, so this in spirit is very similar to this alpha and 1 minus alpha that I showed in the previous slides. So the idea being that you can take alpha very small, or in other words, you can take lambda tilde to be very large.
I don't see that right away. Does it break the symmetry of your S tilde?
Does it break the symmetry?
Symmetry. I mean, the original model of Staffner et al., I think had an O4 symmetry, right? Correct. I mean, was that correct? Yeah. These are basically it was an O4. O4 symmetry. An O4 symmetry. That's correct, I think. And so your Sn breaks these symmetries, no? That's the question. So you're putting in something to solve this ergodicity issue, but you're putting something which is RG sense maybe not allowed.
But yeah, so I want to make it very massive. I want to tune the theory. So if it's a large lambda tilde is actually equivalent to a small g tilde.
But you nevertheless, so I mean, I feel comfortable when I allow, add things in my action, which are going to be symmetry allowed, right? Because I can argue always, if I do some RG or anything, it will pop up somehow. But so the question is, if you add something which is not symmetry allowed, even if it's small, you don't really know what's going to do.
But isn't the interaction that you introduce essentially a Hubbard interaction, right?
Sorry, can you repeat?
S tilde is essentially the Hubbard interaction, is it not?
The attractive one, yes.
Yes.
So that breaks it O4 to SU2, SU2.
No, SO4.
It breaks to SO4, so SU2.
So it only
SU2.
breaks the
SU2
parity.
times SU2, it breaks the parity, right? You maybe don't care, right? You maybe don't care, but you change the symmetry of the.
Yes, but that symmetry I don't think was important for the physics that was yeah.
So this is an attractive.
Yeah.
Do you basically mean that if the mass is too large or if the inverse parameter is too small, then there would be no effective tunneling between the sectors?
Yes, exactly. So if
you have to keep it like small enough so that it moves between the two things, but
yeah, exactly. So if it's too large, then basically phi will not fluctuate. Its expectation value will be roughly like it will just stay around 0. So and then the matrix will not be complex.
Yeah.
So for this icing problem, this basically just I transfer the field icing leaving on the bound coupled to the Fermi surface.
That's the discrete version, yeah.
Right.
Here we're using the continuum phi version.
Sure.
Yeah.
But do you actually see without doing this complete, adding the complex field, you already run into problem by HMC?
We did not even try because we are so certain that we will.
I see.
Yeah.
I see.
And further, testing for ergodicity is a very unpleasant thing. I mean, you're always trying to you're trying to convince yourself that the answer that you're getting is wrong, but sometimes it's right.
Precise with the HMC step, but nevertheless possibly there.
If you take a too large HMC step, then
but I guess the question here is like, do you really, for this spin fermion problem, are you really going to need to cross the barrier? I mean, is there a barrier for you to cross?
In the Ising pneumatic
Yeah,
case?
yeah.
For the same exact reason
Mhm.
that, so yeah, in this paper by Faker and company, they really saw that the barriers had a huge impact. You could not cross them. Correct? This is your paper.
Yeah, I mean, we have a plot.
Yeah, the plot is extremely convincing,
I know, but I'm not sure whether this also applied to the IC pneumatic.
but it's the same
Yeah.
exact
Uh-huh.
construction for getting rid of the sign problem.
Basically, the thing you have to do before starting it, you just have to look at the sign, the average sign of one determinant, right? You just look at one
Yes.
determinant if it fluctuates positive, plus or minus, and in this model it does, right?
Yeah.
So then you know that you have potentially a lot of issues.
Okay. So yeah, so for the reason that I was saying that even though the previous work on the Hatfield-Hubbard model indicates that you can use a very large effective lambda tilde or equivalently a very small g tilde here to make this coupling very weak or these fluctuations very small. This will likely break down at some point near criticality, because it's on principle it shouldn't work. So it shouldn't work infinitely well at large beta and large volume and near criticality. So it might be the case that we need to use some parallel tempering to go between regime that we want, which is very large lambda tilde, and the regime that we can access with no ergodicity breaking, which is small lambda tilde. So yeah, this is work in progress with Sumner, Hirth, and Chris Lauman. Okay, so that's this example of us trying to solve the issues of ergodicity, which pop up sometimes in a very clear way that you know of. And the last thing that I'll discuss is a problem that we've encountered, which we think is likely generic, and we think we understand the issue, the reason for it, which is the sampling in quasi-ordered phases. When the landscape becomes non-convex, the gradient sampling that we do in HMC might need some help. So in other words, like for example, in this O3 spin density wave model that we study, we have some at finite temperature, we have some quasi-long range order. So let's say in the clean case, and what that means is that the potential energy landscape has this gets inverted and has a Mexican hat potential. That looks something like this. And then we expect that this intuitively should limit the step size in your leapfrog integrator to be smaller, just because you kind of are bounded by this large curvature in the trough in the perpendicular direction. You have to traverse that carefully. And what we see in the warm-up phase is that this manifests not necessarily in epsilon shrinking, but actually in the need to solve this, to obtain the hybrid Monte Carlo forces to higher precision. Or in other words, we need to solve this conjugate gradient. We need to solve CG more accurately. We need to solve this linear system of equations more accurately. So this increases the cost. And the same thing we observe happens when we lower the temperature in the disordered case, like at the in the critical phase. So there we expect that superconducting fluctuations are starting to appear, and that would imply that the energy landscape again is becoming not as trivial as it was. And so this is likely the same phenomenon as a quasi-ordered scenario. And so of course we can just bite the bullet and solve the system to higher precision. But it becomes, as you go deeper and deeper into the ordered phase, yeah, it seems like the warm-up really starts to break down due to the fact that you need to go to solve it to larger and larger accuracy. Although we have not tested it, so we don't know if we solve it, we haven't seen what accuracy we need to solve it to, depending on this value of lambda minus, or lambda c minus lambda, that being large. So one potential way around this is to use implicit ODE solvers, which would help us solve these, which would help us traverse these troughs without the need for such absurdly small step sizes. Yeah, I'm not really going to say more about that. That's kind of just some in the works things. Okay, that's the conclusion.
So when the superconductivity sets in, let's say, right, in
Yeah.
the XY case, fermion open a gap. Fermion spectrum open a gap.
Well, they start to sort of open a soft
Yeah.
gap. Yeah.
So I would naively think now this becomes simpler than the critical.
Yeah, if it
Yeah.
actually opens a gap,
Yeah.
yes, but this happens gradually.
Sure, but still there is a, it's still better than a critical system, right?
Yes, when we eventually hit the actual superconductivity,
Right.
that will be the case, but we haven't gone to low enough temperatures to do that.
I see.
Yeah.
So the way how I understand this idea of tuning M in the mass matrix for the conjugate momenta in the HMC, you're essentially trying to diagonalize the field so that you generate these nice circles. But here, like, isn't this kind of assuming that you have some sort of a Gaussian point, which in the Mexican hat you don't? So if you are, say, on the left side of the Mexican hat, you would have to make small circles in the X direction. But while you are in the like side that's facing us, you would have to make the circles much smaller in the Y direction. So is this mass matrix dynamic enough to adapt to where you are in the configuration space, or how is this treated in general?
So
Like,
you would,
does the question make sense?
yeah, it is dynamic enough to adapt to where you are, because you would always be somewhere here, roughly speaking. You would be traversing, like you would not like go up to this guy. But the fact that it has this weird form, this non-convex form, is a problem as well. So we don't know how, we haven't like tested to death how good of a mass matrix it actually, or how bad of a mass matrix it becomes as you go deeper into this order phase. That's also true, yeah. But yeah, it will be more difficult for it to capture all the curvature.
Because I mean, if I was to single out the Q equals 0 moment, the fields that you are plotting, the X and Y component of the Q equals 0 moment, if I have an O2 symmetry breaking, then I guess I would have to rotate the mass matrix depending on where, what's the field configuration that I have.
But it's quasi long range order, so it's never, the mass matrix is never actually ordered. So the correlation function never has explicit or long range order. So it doesn't ever pick a direction. By direction, you mean like actual flavor?
Well, I mean that if I look at configurations that dance around the point where the Y component of the spin is almost 0, and the X component has some finite value. Maybe it's not really long range order, but there is a tendency towards long range order. So I'm close to this Mexican hat potential structure.
Yeah.
Then I would expect that the mass matrix for the field in the X direction is quite different than the mass matrix for the field in the Y direction. Because of the curvature, in one I'm kind of doing the longitudinal mode, one it's more like the angular mode. But
Yeah.
then again, if I was dancing around the configurations where x is 0, these directions rotate.
Yeah. I don't have a.
Matrix is not constant, basically.
Exactly.
Yeah, but
The mass matrix is not independent of the fields themselves.
No, but the correlation function averaged still will not have any specific direction picked out. So then that is the mass matrix. So I'm drawing this schematically, but this is not a good.
Yes,
that's
but then-
not a good
okay,
way of
but then-
thinking about.
But then let me ask the question this way. How much does the averaged mass matrix over the full configuration space help you in finding good trajectories locally from a given starting configuration?
Yeah, I didn't test this. I mean, you're right. This is potential. This is definitely a thing to think about. I don't. Yeah, I don't have a good answer. We did not extensively test this. But yeah, at the moment, it seems like going deep into the ordered phase is a problem. And yeah, it might, the non-convexity of the mass matrix might definitely contribute to this. But also, yeah, the type of solver that you use, I might need to switch it.
So following up on both Johannes' question.
Sorry,
and
but this is only definitely the case. Like we see it for its ordered phase. We believe that due to what's saying said, you can still access the superconducting phase due to the fact that like your fermion, like you can access it more easily due to the fact that you lose the full Fermi surface when superconductivity sets in. There's a
what we saw for the isolated case for the ESS type of simulation is that you can clearly see there's a TKT by marrying the fermion pairing correlator. You can determine the TKT in a finite size, 20 by 20 or 30 by 30 size. And then below that, clearly the fermion at that finite system, the fermion spectrum open a gap.
Yeah,
you can see that.
Yeah,
So
we saw that too.
Yeah,
in the sort of case we had different disordered distributions where we
Right.
saw that like little puddles of depleted density of states affected the overall single particle gap
Yes.
that you observed.
And when that happened, I assume the simulation become easier, not harder.
Yes. Yes.
So
some aspect of it will become easier. The matrix inversion will become easier. Right.
Okay.
Which is kind of your main bottleneck.
Yeah, sure.
So just following up on Johannes' question and also your discussion on ergodicity in the last few slides. So there's one question I had been wondering about, which is, so HMC generally works in continuous fields and all updates are in some sense global. Now, one problem, not just in Fermion Monte Carlo, but all sorts of Monte Carlo, including classical ones, is it's hard to come up with good global updates. So I was thinking if I were to consider something very simple, let's say the classical 3D or 2D Ising model, and then I do a Hubbard-Stratonovic transformation to go into continuous fields. Is there effort, or do you think it's useful to try and come up with HMC algorithms which work as good cluster algorithms in cases we know, not even, let's say, very challenging problems, but because naively, if I just try to do HMC on this, it works as good as Metropolis, but not better. So I was thinking,
is this a fermionic model?
No, but
then
yeah, not fermionic even. But you could think of fermionic models as well, but anyway, there are no cluster algorithms to compare. Good, at least no good ones.
I can't really say much about this model for straight bosonic systems, like the efficiency of them compared to cluster updates. We did apply our method of sampling just to a purely bosonic version in the recent paper. And yeah, it works fast, but I have no idea how like comparatively.
Okay.
Yeah. Okay. Maybe I'll just conclude. Okay, so HMC with auto-tuning in conclusion is a useful alternative for BSS for sign problem-free condensed matter models. And having powerful preconditioners and working on GPUs allows for enormous speedups. And we're actively working on addressing remaining methodological challenges that arise in various situations to kind of try to shore up all the different cases where this is applicable. And my hope is that this method can become universally applicable and powerful, and maybe even eventually just replace the BSS algorithm for sign problem-free models, but not soon. So,
It's a compliment.
yeah, it's a compliment. Yeah. Yeah. Anyways, so thanks for your attention.
Is it we can still ask a few questions? Or not?
I have two questions about the use of GPU. So, which part did you are you using GPU? And also, I'd like to know whether which you use actually CUDA or OpenACC.
We use CUDA.
Yeah, CUDA or
we use CUDA.
CUDA. I see. Okay.
Everything.
And in which part of your calculation you use GPU? I mean, which part is say more effective?
More what? Effective?
More effective, yeah.
So the matrix vector multiplications are done very quickly on a GPU.
Okay.
You can do them in a matrix-free way. You just write the product basically of the matrix times an arbitrary vector.
Yeah.
You write something called a kernel for this object.
I see.
And then when you have an iterative solver like that inverts a matrix, like conjugate gradient, it's an iterative procedure, and the first few iterations, you don't care that how accurately you solve them. And so you can use lower precision to solve the first several iterations. And lower precision arithmetic is extremely fast on GPUs. So there's a big speed up there.
Okay, thank you.
And then we switch to double precision, but the point is that you don't have to do all of the iterations in double precision.
If you have no questions, we can have coffee break.